Okay, so now the question continues. What's the wavelength and frequency of the light in lucite? And in the last problem, we just figured out that this was 1.9. Let's see, this number is rounded. That just won't do, right? So 98675 times 10 to the 8th meters per second. And that's something that I've stored in my variable A. At least now I have. All right, so there we go. And then what is the wavelength and frequency of the light in the lucite? So the key concept here is that the frequency stays the same. So whatever the frequency is in the air, it's the same frequency in the lucite. Frequency stays the same, but the wavelength is going to get shorter because the velocity gets shorter. All right? So I'll just show you, let's figure out the frequency first. This is using V as F lambda, right? And so the frequency will be the same frequency that it is in air, where this is the wavelength, right? So let's figure that out. So 3.00 times 10 to the 8th meters per second is the speed, because that's essentially the speed in air, right? And then the frequency is what we don't know. The wavelength is 640, and then a nanometer is 10 to the minus 9th, right? So times 10 to the minus 9th, right? So if I go 3e8 divided by 640 e minus 9, I'm going to store this, by the way, in my location B on my calculator, right? I get the frequency is 4.6875 times 10 to the 14th hertz, right? This is 10 to the 14th is Bugala hertz, right? So you could just say 4.69 Bugala hertz, right? Save you a little bit of writing there, right? Okay, so now it's like a capital B. It's like Bugala hertz. All right, now, and then we want to find the wavelength in the lucite. Well, now we can use the same formula again, right? V is equal to F lambda, right? Only the velocity is this velocity, right? Because it slows down when it gets into the lucite. So 1.98675 times 10 to the 8th meters per second equals this frequency, right? 6875 Bugala hertz. And then that's times the wavelength, right? So I can just divide the answer from A divided by B, right? And I get that the answer is 4.238 times 10 to the minus 7th meters, right? Which would be 423.8 times 10 to the minus 9th meters to keep it in nanometers, right? So that's why it says 424 nanometers, right? And it's nanometers is a standard way to talk about light waves. We always talk about it as nanometers. That's why I kept it in nanometers. You don't have to. This is just a fine answer. Okay. The other way, by the way, to find, and this is the alternative ending, right? The other way to find your wavelength, right, is you can just simply totally bootleg this, right? You know it's going to get to be a shorter wavelength because the velocity decreases. You know it's all direct proportions, so the new wavelength is just 640 divided by 1.51, right? So 640 divided by 1.51 is 423.84, exactly the same number, right? Okay, nanometers, right? Because this was nanometers. So this is the proportion, the index of refraction is how much, or the ratio of the indices of refraction is the amount by which the velocity slows, and also the amount by which the wavelength decreases, right? So either one of those will work. Got to draw my smiley face there.